For 150 years, every single engineer who ever tried to build a gasoline engine ran headfirst into the same brutal wall. You burn fuel inside a metal cylinder, and most of that energy simply disappears. Not into motion, into waste. Heat you cannot use, friction you cannot avoid, pressure that leaks away before it ever pushes a piston. Toyota spent more than 2 decades and untold billions of dollars trying to chip away at that wall. And for years, nobody could touch what they built. Then, in the spring of 2026, a Chinese automaker that used to manufacture refrigerator parts announced a number that stopped engineers around the world in their tracks. And barely 2 months later, one of its domestic rivals quietly beat that number too. So how did an industry that moved at a crawl for a century suddenly start breaking records every few weeks? Stick with me, because this story has more twists than most people realize. And by the end you'll understand why the humble gasoline engine, the thing everyone keeps declaring dead, might actually be living through its most explosive era of innovation ever. Where it all began. Rewind all the way back to Cologne, Germany. In 1876, a German engineer named Nikolaus Otto had spent years chasing an idea that other inventors had already given up on. An engine where intake, compression, ignition, and exhaust all happened inside one cylinder, in a controlled repeating cycle. The concept wasn't brand new. Back in 1860, a French engineer named Étienne Lenoir had already built a working gas engine. It ran, but it never compressed the fuel-air mixture before lighting it. The result was an efficiency figure so low it's almost hard to believe, less than 5%, for every unit of energy packed inside the fuel. Less than a 20th actually turned into useful motion. Everything else vanished, absorbed by the metal, lost through vibration, bled away through the surrounding air. Otto believed compression was the missing piece. He spent years testing, refining, partnering with industrialist Eugen Langen, and in 1876 he finally proved himself right. His 4-stroke engine compressed the mixture before ignition, and it reached somewhere between 12 and 15% thermal efficiency. That number sounds laughably small today, but compared to Lenoir's design and to the steam engines dominating the era, it was nothing short of revolutionary. His operating principle became so foundational that engineers still call it the Otto cycle a century and a half later. But here's the part that should genuinely frustrate you. For the next 100+ years, progress crawled. By the early 1900s, efficiency crept into the high teens. By the middle of the century, the best production engines were pushing past 25%. Decades of investment poured into fuel injection, turbocharging, variable valve timing, exhaust gas recirculation, computer-controlled combustion, and by the 2000s, a well-engineered production engine might reach 30 to 33%. Better, sure, but after over 100 years of relentless effort, barely better. Why progress nearly stalled? The reason isn't laziness or lack of investment, it's physics itself. A principle called the Carnot limit sets a hard theoretical ceiling on how much usable work any heat engine can extract from the temperature difference between its hottest and coolest points. For a real-world gasoline engine, that ceiling sits somewhere around 60%, but no production engine gets anywhere close, because friction between piston and cylinder wall. Incomplete combustion, exhaust heat carried straight out of the tailpipe, and heat absorbed by the coolant system all attack the engine simultaneously. Each loss compounds the others. And the closer engineers get to the ceiling, the steeper and more stubborn it becomes. For decades, reaching 35% in a mass-produced car was considered a genuine engineering triumph. 40% looked, to a lot of very smart people, like a wall that might never fall. One company refused to accept that, Toyota's 2-decade obsession. If you had asked anyone in the automotive world in the early 2000s which manufacturer would push combustion efficiency the furthest, almost everyone would have given you the same answer. Toyota had spent decades building a culture of relentless, incremental improvement, a philosophy known as Kaizen, and applying it to literally every component, every tolerance, every step of assembly. When that obsession turned specifically toward thermal efficiency, it redefined what the entire industry believed was even achievable. In the late 1990s, Toyota launched an enormous internal overhaul called the Toyota New Global Architecture. The ambition was staggering. Consolidate a sprawling lineup of more than 800 engine variants down to fewer than 20 highly optimized designs. It sounded almost reckless for a brand, famous for offering something for everyone. But the logic was sound. Fewer platforms meant deeper investment in each one, and deeper investment meant real breakthroughs. The crown jewel of that strategy was the dynamic force engine family. When the first version landed under the hood of the 2018 Camry, the industry took notice. The 2.5-liter inline-4 gasoline engine hit 40% thermal efficiency, its hybrid variant. Running a 14:1 compression ratio on the Atkinson cycle, reached 41%. Both were the best numbers ever recorded in a production car engine. What made it even more impressive was everything hiding underneath those two numbers. Toyota redesigned the intake ports to create a fast, tumbling airflow pattern for more complete combustion. They widened the angle between intake and exhaust valves from 31 to 41 degrees, opening a straighter path for incoming air. They lengthened the piston stroke relative to bore diameter, giving each combustion event more time to push the piston. They coated the pistons to cut friction, installed an electronic thermostat and electric water pump for precision coolant control, and deployed a dual fuel injection system that toggled between port and direct injection depending on driving conditions. Every one of those changes sounds small on its own. Together, they represented roughly 20 years of concentrated research, and for years, nobody in the world could match it. A refrigerator parts salesman enters the chase. While Toyota was refining engines in Aichi Prefecture, something completely different was unfolding in a coastal Chinese province called Zhejiang. In 1986, a 19-year-old named Li Shufu borrowed money from his family and started a tiny business in the city of Taizhou. He'd just finished high school, bought a camera with his graduation money, ran a small photography studio for a while, then pivoted into something far more industrial, manufacturing refrigerator parts. Simple metal and plastic components. Nothing about that workshop hinted at what was coming. When tightening regulations forced his refrigerator factory to close, Li didn't walk away from manufacturing, he walked deeper into it. In 1993, he spotted a struggling state-owned motorcycle factory, acquired it, absorbed its production knowledge, and started building his own motorcycles and scooters. Within a year, he was selling tens of thousands of units annually across southern China. Then he made a move almost everyone around him thought was reckless. He announced he was going to build cars in 1997. He founded what became China's first privately owned automaker, even though Beijing had explicitly stated no new passenger car manufacturers would be approved. He applied anyway. Rejected, he bought land under the pretense of expanding motorcycle production and quietly built an assembly plant behind the scenes. His first car rolled off the line in 1998. Built heavily around a Daihatsu design, using knowledge scraped together from a disassembled Mercedes-Benz and a Chinese-built sedan he'd bought purely to reverse engineer. It was rough, inconsistent. Nobody in Detroit, Tokyo, or Stuttgart paid it a moment's attention, but it was cheap, and it put ordinary Chinese families behind a wheel for the first time. And for Li Shufu, that was enough to keep going, the deal that changed everything. The real turning point came 12 years later, in 2010. When Li's company signed a deal worth $1.8 billion to acquire Volvo Cars from Ford, the largest overseas acquisition ever made by a Chinese automaker at the time. Western analysts were skeptical, almost dismissive. Could a company that had been stamping refrigerator parts 24 years earlier really manage a premium Swedish brand? What those observers missed was what the deal actually delivered. Li wasn't just buying a badge or a dealership network. He was buying decades of accumulated powertrain engineering, crash safety research, and manufacturing discipline, and all of it began flowing straight into his own research pipeline. The two companies formed a joint powertrain operation, combining engine development resources into a single unit. By 2024, that operation had grown into something far bigger, a joint venture between the Chinese automaker, Renault Group, and Saudi Aramco, employing 19,000 people across 18 manufacturing plants and 5 research centers on 3 continents, producing roughly 5 million powertrain units a year and supplying engines to Volvo, Nissan, Mitsubishi, Proton, and Renault itself. When Saudi Aramco, an oil company, takes a 10% stake in a combustion engine venture, that alone tells you something about where the smart money believes the internal combustion engine is heading. This wasn't just vertical integration. It was the construction of a global engineering ecosystem that could go toe-to-toe with anything the century-old automotive establishment had built. And this company was far from the only one racing toward the same target, the sprint nobody predicted. By the middle of 2024, an unofficial arms race had broken out across Chinese automakers, and the pace of it caught the entire global industry off guard. This wasn't the slow, careful, incremental competition the industry was used to. It was a full sprint. with multiple manufacturers leapfrogging each other's announcements within days of one another. In May 2024, one manufacturer unveiled a fifth-generation hybrid system with a dedicated engine certified at slightly above 46% thermal efficiency, clearing Toyota's long-standing 41% record by a full 5 percentage points. A gap the rest of the world had spent decades failing to close by. Even a fraction suddenly evaporated in a single announcement, backed by certification from a national testing authority. A rival's response came within days, a competing certification just above that figure. Then another update pushed the claim even higher, for an engine still in development. Two of China's biggest automakers were trading records back and forth like fighters exchanging blows in the opening round of a title fight. If you want to see exactly how far this race has come and where it's heading next, you might not want to miss what happens later in this story. So consider following along for the rest of the breakdown, because the numbers only get wilder from here. By October 2025, another major group announced it was developing an engine specifically targeting 48%. Here's why that number matters commercially, not just academically. Every single percentage point of thermal efficiency gained translates to roughly a 2.5% improvement in real-world fuel economy. So these announcements weren't just bragging rights. Whoever delivered the most efficient hybrid stood to capture serious market share, not just domestically, but across Southeast Asia, Europe, and eventually markets in the Americas. 2 months later, another automaker's turbocharged 1.5-liter engine was certified above 48%, pushing the frontier further from where Toyota had planted its flag just a few years earlier. Every record felt temporary the moment it was announced. Here's a comparison that puts the sheer speed of this into perspective. According to Nissan's own published research, it took the global auto industry roughly 30 years to move thermal efficiency from 30% up to 40%. 3 decades of concentrated effort from every major manufacturer on the planet. Chinese engine laboratories were stacking comparable gains within months of each other. What took the rest of the world an entire generation, they were compressing into a single calendar year. The record that broke the internet then came April 13, 2026. At a launch event in Hangzhou, the automaker built from Li Shufu's original refrigerator parts workshop unveiled a new intelligent hybrid system. The headline figure: 48.41% thermal efficiency, independently verified by Guinness World Records. Not a concept demo, not a laboratory curiosity, a production-ready powertrain. Built for cars shipping to dealerships within weeks, the system paired a 1.5-liter naturally aspirated engine, producing 82 kilowatts, with a dual-motor P1 plus P3 hybrid layout and an integrated 11-in-1 electric drive unit delivering up to 230 kilowatts, roughly 308 horsepower, from the electric side alone. Under standard testing conditions, the electric system handled more than 80% of driving scenarios, keeping the combustion engine off unless conditions genuinely demanded it. And when the engine did fire, it stayed locked into an extraordinarily narrow, high-efficiency band. Thanks to a combustion system the engineers nicknamed the Windride Tornado, refined fuel-air mixing and combustion chamber geometry, designed to extract the maximum possible energy from every single ignition event. Now here's where the details most people skip right past actually matter. To hit that number, engineers used what's called a duckbill air intake shape, a stroke-to-bore ratio of 1.39 to 1, a compression ratio of 15.5 to 1, peak fuel injection pressure of 500 bar, and a 150 millijoule ignition system paired with Miller cycle valve timing, on top of the combustion improvements. Friction losses inside the engine were cut by over 16% through precision grinding diamond-like carbon coatings on internal components, and lower viscosity engine oil, squeezing out an additional gain that alone added roughly 0.4 of a percentage point to overall thermal efficiency. Small on paper, nearly impossible in practice. The fuel economy numbers were even harder to believe. During a controlled highway loop test on Hainan Island, the sedan carrying this powertrain, the 5th-generation Emgrand iHEV, recorded 2.22 liters per 100 kilometers. Guinness certified that as the lowest fuel consumption ever measured in a mass-produced hybrid vehicle. In American terms, that's roughly 106 miles per gallon. The company claimed the result beat a Toyota Prius on the same route by more than 12%. There's more buried in the fine print that almost nobody talks about. The system runs on what the company calls an AI cloud power model. sensing outside temperature, humidity, altitude, and even road gradient in real time. Automatically choosing the optimal split between gasoline and electric power, a feature the company says improves comprehensive energy efficiency by more than 10% on top of the hardware gains. Engineers also built in active engine stop position prediction and noise cancellation technology, cutting startup vibration by nearly a third. So that total cabin refinement measured only about 1 decibel higher than what you'd get in a fully electric vehicle. On June 16, 2026. This car went on sale in China, starting at roughly $13,000 a sedan, carrying arguably the most thermally efficient mass-produced gasoline engine ever documented. Priced below a base Honda Civic in the American market. And then somebody beat it. Here's the part almost nobody outside the industry is talking about yet. And it's arguably the most important twist in this entire story. That record didn't even last 2 full months in June 2026 at the Shenzhen Auto Show. A rival Chinese manufacturer, the same company that once built its reputation exporting more vehicles overseas than any other Chinese brand, unveiled its own hybrid engine, using a hybrid dedicated system built around what it calls a dual curve. Triple link mechanism, officially certified thermal efficiency, 48.57%, a new global record, edging past the number that had made headlines just weeks earlier. Around the exact same window, a third major automaker introduced a competing hybrid architecture featuring the world's first mass-produced 500-bar direct injection system, hitting just over 44% while promising sedans that sip fuel at barely 2 liters per 100 kilometers in city driving. Even a fourth manufacturer, better known internationally for building rugged pickup trucks, is now pushing engines above 41% while quietly preparing next-generation diesel hybrids for global export markets. Japanese business media has openly acknowledged what's happening. Multiple Chinese engine platforms have now measurably surpassed the best that Japanese manufacturers long considered the gold standard of combustion efficiency currently produce. One widely cited comparison put a leading Chinese hybrid engine 3 full percentage points ahead of Toyota's best current hybrid system and 7 percentage points ahead of Honda's. If a story like this genuinely surprised you, imagine how fast this space is moving behind the scenes right now. New certifications are being announced practically every quarter. That's exactly the kind of ongoing story worth following closely. So if engineering breakdowns like this one interest you, sticking around for future updates means you won't miss the next record when it inevitably falls. What this actually means. For years, the dominant narrative in the auto industry has been that internal combustion is a dying technology, destined for total replacement by battery electric vehicles. There's real truth in that direction for certain markets and certain use cases, but what this efficiency race has proven is something far more nuanced than a simple obituary for gasoline. The combustion engine isn't disappearing, it's being reinvented as a supporting player inside hybrid systems, optimized to run only inside its narrowest, most efficient operating band. While electric motors absorb the exact driving conditions where traditional engines waste the most fuel. Stop-and-go traffic, low-speed acceleration, city crawling. Toyota actually understood this principle earlier than almost anyone else on Earth. The original Prius, launched back in 1997, was built around precisely this idea: let the engine run only when conditions favor it, and let the electric system handle everything else. That concept reshaped how the entire industry thinks about powertrains. What's changed dramatically is that Chinese manufacturers took that same foundational idea and pushed the raw efficiency of the engine itself far beyond anything Toyota's own hardware has managed to deliver. Even as Toyota continues refining its own hybrid systems in parallel, consider the internal trajectory of just one of these companies. In 2021, their platform hit 43.32%. The next-generation architecture pushed that to 46.5%. By 2025, AI-driven energy management brought it to 47.26%, and in 2026, an upgraded combustion architecture reached 48.41% before a domestic rival leapfrogged even that number weeks later. Each jump required solving an entirely different set of engineering constraints. From injection timing and exhaust heat recovery to combustion chamber airflow and fuel-air mixing ratios. None of it happened by accident, and none of it happened in isolation. It's the direct product of deliberate, sustained investment in powertrain research, anchored by acquired engineering expertise and amplified by partnerships spanning 3 continents. The pace itself deserves a moment of real reflection. Toyota's dynamic force engine took roughly 20 years of focused development to reach 41%. One Chinese manufacturer went from 43 to 48 in 5 years. Another then broke 48.5 in a matter of weeks after that. That difference in velocity reflects something genuinely new in how engine development is being conducted, not slow. Sequential iteration, but multiple research programs running in parallel, competing fiercely against each other, and deploying results into showroom-ready vehicles faster than traditional Japanese and European development cycles have ever allowed. To put the ceiling itself in perspective, modern Formula One power units, arguably the most sophisticated engines ever designed for any purpose on Earth, operate around 50% thermal efficiency. Those are unlimited budget racing engines, built without any constraint on cost, weight, cabin comfort, or production volume, refined by teams spending hundreds of millions of dollars per season. Chinese automakers are now approaching that exact same territory inside family sedans that cost roughly what a 5-year-old used truck sells for in most American markets. Nissan has already demonstrated 50% efficiency in laboratory conditions using an architecture where the engine works purely as a generator and never touches the wheels directly. Multiple other manufacturers reportedly have programs targeting figures beyond 49% already in development. The race is nowhere near finished, and the ripple effects are already visible in the market. 2 legacy European manufacturers have watched their sales inside China decline by 80%, and roughly a third respectively from peak levels. Even Toyota, which has weathered the shift better than most foreign brands, has still seen its China sales drop by 14% from its high water mark. The ground underneath the entire global auto industry is shifting, and this efficiency race is just one visible, measurable symptom of a much bigger transformation already well underway. Li Shufu started out assembling refrigerator components in a small workshop in Taizhou 4 decades later. The engines emerging from his company's research labs, and now the labs of his fiercest domestic rivals operate at efficiency levels that would have sounded like pure engineering fantasy back when he was bolting together kitchen appliance parts. He once told reporters that his dream was simply to build good cars ordinary people could actually afford, a record-breaking Guinness-certified engine inside a sedan priced around $13,000 answers that promise in a way almost nobody saw coming. The internal combustion engine has been around for 150 years. What it's actually capable of is still being rewritten, month by month, by engineers who weren't even part of the global conversation a single generation ago. If you want to see exactly which company breaks the next record, and it's probably closer than you think, following along for the rest of this series is the easiest way to catch it the moment it happens.